Morning, everybody. Welcome to today's talk. Today, we're very delighted to have Professor Chris Hall from Imperial College London. And of course, everybody should know Professor Chris Hall. But I'll mention some of his accomplishments. So, Professor Chris Hall is the chair professor of theoretical physics at Imperial College London, Faculty of Natural Sciences. And he's a fellow of the Royal Society, and he's also a recipient of, the most prestigious, one of the most prestigious, the Dirac Medal. So without further, delay, please join me welcoming Professor Chris Hall talk, this super interesting talk, and the action for the superstring field theory. So Professor Hall, please take it away.
Thank you very much. So in this talk, I'm going to, as the title suggests, present a new action for the superstring field theory. So let me start by making a few comments about string field theory. For the description of particles, it's, as we all know, it's been very fruitful to go from a particle to a field theory description, and we all know that quantum field theory has been a hugely successful approach to particle physics. And the idea in string field theory is to move from a worldsheet first quantized description to introducing a string field, something which would play the analog of the field in quantum field theory, but for the string. Now, a string spectrum consists of an infinite set of particles, some massless particles and an infinite tower of massive particles, and maybe a tachyon in the bosonic string. And the idea is that one way of thinking about this string field is it's a generating function which encodes an infinite set of fields, including the graviton, the dilaton, plus an infinite set of fields with arbitrary masses and arbitrary and complicated sets of indices. And the idea is to introduce an action which governs the dynamics and which is invariant under various symmetries in such a way that that one way of interpreting that is it will then generate an action and symmetries for the component fields. So it's a way of understanding the string as a whole rather than the approach of, for example, supergravity and low energy effective field theories, which just focuses on a small part of the story. So one of the features is it gives rise to an approach to string perturbation theory involving some stringy Feynman diagrams. And an important part is that the string field theory should be set up in such a way that it recovers the familiar string amplitudes which we know and love from perturbative string theory. One of the advantages of a field theory approach is it allows a systematic treatment of infrared divergences, unitarity, questions of ultraviolet finiteness, and a systematic study of, for example, mass renormalization. And as a non-perturbative formulation, it would one could use that to look at solutions and phenomena such as tachyon condensation. And these sorts of applications are something which has been a lot of very interesting work done recently, most notably by Ashok Sen and his group. So in this approach, things like Nerva-Schwarz five-branes and Klutz-Klein monopoles would arise as solitons of the string field theory, in principle, and D-branes would arise from introducing open strings with the boundary conditions. And this approach has been recently used quite very successfully by Ashok Sen and collaborators for studying issues to do with, for example, d-instantons. And one of the features is that the string field theory fixes some of the ambiguities and vagaries which are there in the worldsheet approach. But in trying to use this approach for the superstring, as opposed to the bosonic string, there are a number of technical issues which arose. One was it appeared that there was no way of constructing a kinetic term for string fields in the Ramond sector. One of the things I'm going to show on the next slide is how to do it, but one of the formal difficulties which was appearing in the earlier literature is that people weren't sure how to write down such a kinetic term. And I'll say a little bit more about why and how to get around that in a moment. And one thing is, as I mentioned, the string field theory will give rise to field theories for the component fields. And the 2B string, amongst other its massless fields, has got a Ramond-Ramond 4-form gauge field with self-dual field strength. So G is the 5-form field strength. And a 2B superstring field theory would, amongst other things, give an action for this gauge field. But constructing a consistent action for a self-dual gauge field is a long-standing problem. So any solution for how to write down a superstring field theory, in particular the issues arising in the Ramond-Ramond sector, would be go hand in hand with an issue about solving this problem. And a solution to both these issues was brilliantly found by Ashok Sen, and his idea was to introduce two string fields, psi and psi tilde. This then allows a Ramond sector kinetic term, which I'll write down a bit later. And because there's two string fields, this gives rise to two superstrings. One is the physical interacting superstring we want, which includes a graviton. And then there's a second thing which comes along, which in Ashok's theory is a free string theory. And importantly, it decouples from the physical fields. And that decoupling means that we get a self-contained treatment of the physical stuff. And then there's this extra stuff which comes along for the ride, which enables us to write down the action. And because it doesn't couple to the physical field, in particular, it doesn't couple to the graviton which sits in there. So we've got the strange situation of having some fields which don't couple to gravity, which raises a lot of formal issues, which I'll talk about in a moment. But this action then gives rise to a solution for action for self-dual gauge fields. And starting from two string fields, he ends up with two self-dual gauge fields. There's the physical field C arising from the physical string, which interacts with gravity and the other physical fields and sits in the supergravity multiplet. And then there's a second one, which decouples from gravity, decouples from all the physical fields, and decouples from this other one. So it just goes along for the ride, enables one to write down the action. And in Sen's approach, this only couples to a background Minkowski metric. And this theory has a diffeomorphism-like symmetry arising from the gauge symmetry of the string. But under this gauge symmetry, the physical gauge field and the metric transform as one might expect, but the second gauge field doesn't transform at all, which is a very bizarre story. So, as I mentioned, this theory involves a Minkowski metric, and one of the problems is that you can't put a Minkowski metric on an arbitrary space-time. It's only on very special space-times. And under a change of coordinates, all fields must transform because they depend on the coordinates. So, in particular, all fields must transform under diffeomorphisms, and to formulate the theory, one would want all fields to transform under diffeomorphisms. And hand in hand with that is the idea that all fields should couple to gravity, and that's intimately related with the equivalence principle and so on. And so there's a question about what to do, what does that mean for the second gauge field, which decouples from gravity and doesn't transform under the diffeomorphism-like symmetries. And finally, yeah, and we'll see that in a moment. Yeah, and so one of the issues which I'm going to say, which is going to be one of the themes, is what's going on when you've got two gravitons. And the second gauge field also has negative energy in a certain sense. If you look at, you see the way it enters, it comes in with various wrong signs. And so it's probably just as well it doesn't couple to gravity. If one did, then there would be an unstable system. So some of these problems for the self-fuel gauge fields I looked at a couple of years ago, where I replaced the Minkowski metric with a second metric. So we ended up with a formulation with two independent metrics, which meant that it could be put on any space-time. And then we ended up with two sectors, a physical sector, which includes all the physical fields, a shadow sector, which has decouples from the physical sector. And introducing this extra graviton, then the symmetry structure became clearer. In particular, there were two diffeomorphism-like symmetries, one for each sector. So here we've got two spin-2 gauge fields, and so there's a spin-2 gauge symmetry for this field and one for this field. And in this story, the real diffeomorphisms, which related to coordinate transformations, sat as a diagonal subgroup, and which acted on all the fields. But because there were two metrics, there was, as well as the diagonal subgroup, there was one more independent symmetry, which could be taken as this one or this one. And this biometric geometry led to novel couplings. The way covariance is achieved involved structures which are not familiar for many of the usual story, and there was a resulting action was nonlinear in both metrics in a rather surprising way. And in this story, the geometric approach gave an understanding of this. In Sen's original work, he constructed these couplings perturbatively, but by studying the biometric geometry, it was possible to get a closed form understanding of these things. So what are the implications of this for this superstring field theory? So Sen's superstring field theory gives the correct quantum calculations for the amplitudes for the physical superstring, so there's, which is very important. And this was a very non-trivial part of his construction. So that's certainly something one would want to maintain in any generalization. As Mahmad and Svibak showed, it gives precisely Sen's action for the self-dual gauge field plus its shadow. And it has transformations which they referred to as exotic diffeomorphisms, ones which only fields from the physical sector transform, but some of them transform in a strange way. In particular, some of them under these transformations, for some fields, they transform into other fields. And the fields from the other sector are invariant. And there's a question about what this has, whether this theory really does have real diffeomorphisms, which, as I've argued, any field theory must have. There must be some. Any field must change under changes of coordinates. So it's a question about how these exotic transformations are related to real diffeomorphisms. And what I've just shown you in this the self-dual gauge field story, one might want to understand. What I want to try and do is show how some of that story extends to the full superstring. And also, this action depends on a choice of background. Just like in the self-dual gauge theory, there was a background Minkowski metric. And this restricts the applicability, and it means that it's not the action, you get a different action for each background in a sense. So what I'm going to present is a new superstring field theory, which looks like Sen's, but it's got some extra terms. It reduces to Sen's in a certain limit. It gives the correct quantum calculations for the physical superstring, as it should. And it has two superstrings, one physical and one shadow, as Sen's does. They decouple from each other. But whereas for Sen, the shadow one was a free theory, here it's self-interacting. And it's this which unlocks the secrets of the gauge symmetry, and in particular allows the theory to be background independent and to have real diffeomorphism symmetry. because there's two gravitons, there are two exotic diffeomorphism-like symmetries, one for each gauge field, with the real diffeomorphisms arising as a diagonal subgroup. So that's the story I want to tell you, and now I want to start saying a little bit, going into a little bit more detail. So starting off with the bosonic free string field theory, the first idea people tried was thinking of it as a functional loop space. But that didn't seem to be so useful, and progress wasn't made. And then Warren Siegel came up with the interesting idea of thinking about the string field as a state in the first quantized string theory, and then writing down an action which involved the BRS charge of the first quantized theory. And then the field equation which came from this was that Q psi equals 0, and the gauge symmetry was like this. So the solutions modulo gauge symmetry gave precisely the BRST cohomology classes, in other words, precisely the physical states of the string. So the starting point was a first quantized string theory, which required a matter conformal field theory with C equals 26, the usual BC ghosts, and then there was a BRST charge. And then a state in the Hilbert space could also be, for each state in the Hilbert space, there's a corresponding operator. And so the string field could be either thought of as the state or as the operator, and I will switch between the two pictures. So if one introduces a basis for the Hilbert space, a basis of vertex operators V I of X, where I is some label of the set of vertex operators, then the string field could be, roughly speaking, thought of as a sum of this kind, where you introduce a field for each vertex operator, and then you'd integrate over position and sum over the set of states. So this way we get a set of space-time fields. And one way of thinking about the string field is as it's a generating function for this set of space-time fields. And as often with generating functions, one can do interesting manipulations of the fields by manipulating the generating function, and this is what's happening. And the manipulations of the generating function are all to do with using the background conformal field theory to manipulate the vertex operators. Then the field equation then gives rise to field equations for each of the individual fields, and the gauge symmetry gives rise to gauge symmetries for each of these individual fields. So the string field, so in this state space, because there's ghosts, it's a graded vector space. The string field is taken to be Grassmann even and ghost number 2. And moreover, it's taken to be annihilated by these two objects. So these are the zero modes of the anti-ghost. And then this action is defined by an inner product, which is defined to be the BPZ inner product of conformal field theory, but with an insertion of the ghost zero modes, where this is the difference between the left and the right moving part, as usual. And for example, for a graviton in 26-dimensional Minkowski space, where the conformal field theory is taken to be 26 free bosons, x mu, then this term here is the standard graviton vertex operator, ghost number 2, and then here we have the graviton field here. I've written this down in momentum space, and then integral over x has become an integral over momenta, and we get this component of the string field. And so the generalization to the closed string theory, to the interacting theory, was very non-trivial and was done some time ago by Barton Spivak. And it ends up with a non-polynomial theory with interactions. And to define the interactions, one introduces a set of n brackets for n equals 1, 2, 3, up to infinity, which is a map from the n vectors to a vector. And for the one bracket, it's defined simply to be the map from which takes a vector to the BRS charge acting on that. And these satisfy an algebra known as it's become known as an L-infinity algebra. So there are, for these set of n brackets, there are generalizations, they're analogs of Jacobi relations, Jacobi identities, but involve, so as relations involving a sum of nested brackets. And this is a key part of the algebra of the story. And in fact, this algebra, which has now become quite pervasive, was discovered for the first time by Spivak in this context. And in addition, using this bracket, we can define a map from n vectors to a number, given by taking this inner product. And this product is defined in relation to the conformal field theory, that roughly speaking, this is related to taking a two-sphere with n punctures, inserting each of these states at these n points, and then calculating the correlation function. It's a little bit more complicated than that, but roughly speaking, this gives that story. And this n bracket is then thought of as you take one of these slots as open, and you look at the state prepared by these n-1 other vectors as giving a new state on the final slot. And then this notation, when these are all equal, and I'll use this notation. And this is the interaction which is occurring here. So these brackets are all graded commutative, but because of these Jacobi-like relations, this story is highly non-associative. And I'll be writing things down in a very condensed notation where I'm leaving off a lot of the brackets, but the non-trivial relations involve putting the brackets in and checking things more carefully. So this action gives rise to a field equation which looks like this and involves these n brackets, and it has a nice gauge symmetry. So all of these look a bit like some higher dimension, some generalization of a Chern-Simons type theory, but one where you have a more general kind of algebra than a Lie algebra. And one can see that how gravity arises from this. One can take the graviton vertex operator, stick it in the string field theory action, and get an action for the graviton. That, in fact, gives the wrong answer. That's too naive, because it turns out that this vertex, state mixes with certain other auxiliary field states. The full calculation I did in the paper with Barton's feedback a while back. And then so if you look at the full calculation with all the auxiliary fields, stick that in the action and then eliminate the auxiliary fields, in the end, one ends up with the familiar gravity action, plus corrections involving kappa coming from this term involving a coupling constant kappa. And we checked to cubic order that this agrees with Einstein's action. We also included the dilaton and the B field. And moreover, the gravitational gauge symmetry arose at least to this order from the superfield gauge symmetry. Although the story to higher orders is much more complicated. This was shown as has been argued by Spivak and Marmot recently. H, you mean the kappa? Yeah. So there's a long story. So there's a question about what you integrate out. When you integrate out massive fields, you'll generate alpha prime corrections. So here I was just talking to lowest order. What I showed was the lowest order in kappa and the lowest order in alpha primed. Yes, so it's a question about constructing an effective field theory from the full string theory. So, because there's all these massive modes, where the mass is governed by alpha primed, when you start integrating out massive modes, you're going to generate higher derivative correction to the effective action. Yeah, thanks. Yep. Yeah. Yeah. Yeah, so in this story, this is just so the actual calculation was actually quite long, and I haven't presented it here, but there's various field redefinitions and gauge fixings, as well as eliminating auxiliary fields to get it to the standard form. And in particular, when you look at the string field gauge symmetry, it turns out it doesn't come out on the nose. It's mixed in with various field-dependent gauge transformations at higher orders. But to lowest order, one gets the linearized gravity coming out in the right way, or to lowest order. So the story is quite complicated. It's only been checked by us to cubic order in the graviton, and there are big formal problems in principle, about the calculation, looking at the quartic and checking how things work in detail there are already quite hard, and that hasn't yet been done. So I think there's a lot more to be understood about how gravity sits inside the string field theory, but at least to lowest order, we're getting reassuringly getting the stuff which we'd expected. So Sen's superstring field theory works in principle in a similar way, except one's going from conformal field theory to a superconformal field theory. So as well as the BC ghosts, you've got super ghosts, or their bosonized version. And in the superconformal field theory, there are a number of quantum numbers. There's a picture number, a ghost number, and a parity under a GSO operator. So it's useful to introduce the notion of the Hilbert space of states with left-moving picture number P and right-moving picture number Q. And then Sen's theory involves two string fields, which are both Grassmann even and ghost number 2, and they're even under a GSO projection. There are two possible definitions of the GSO projection, of the GSO operator, one of which gives 2A theory, the other 2B theory. And then these fields live in these Hilbert spaces. So basically, in the Nerva-Schwarz sector for the left and right movers, they always choose picture number -1. And for the Ramond sectors, we choose -1/2 for this field and -3/2 for this one. And one of the reasons why the issues with the inner product is that for the natural inner product, there isn't, the inner product doesn't work between states of picture number -1/2 with themselves. But for picture number -1/2, you get a non-trivial correlator with something of -3/2, or with -1 and -1. So the whole thing has to add up to -2 on both sides. And the fields are also, as before, in the kernel of these operators. And then Ashok's action, Sen's action looks like this. So we've got a non-perturbative coupling as before, a non-polynomial coupling. Here we have the basic kinetic term psi tilde q'd psi, and another term here. And here, one of the issues is, so here we see one of the formal complications. There's an operator which maps the space of the tilted fields to the untilted fields, which acts as one on the Nerva-Schwarz sector, but involves picture-changing operators on the other sectors. So here, chi0 is the zero mode of the picture-changing operator, and on the left, for the left movers, and chi bar 0 for the right movers. The details won't be important here. As I was suggesting, the conformal field theory is really a black box for manipulating these strings fields, but will be useful this is important part of the story. And this structure is very important in understanding how this gives rise to the right superstring amplitudes. And it has these gauge symmetries. which are looking a little more complicated than the usual, the bosonic story. And there's one of the field equations, we have this field equation, and if in the sector where G equals 1, the never short sector, this is the same form as for the bosonic string. And if we define psi hat as the in this way between the two fields, then this turns out to be a free field, and we get this is a free string, and this has this very simple gauge transformation. So we're getting an interacting string, which will contain an interacting gravity, and plus a free string in the shadow sector. So if we look at the graviton action, introducing a vertex operator for the graviton sitting in the physical string and one in the tilde string, we got two fields H and H tilde, and then the action one gets after a bit of work involves introducing the difference between these two fields, and we get two graviton actions, one with the wrong sign, and two gauge symmetries, lambda, one with lambda and one with lambda hat. So this generalizes to, so this was based on looking at strings in 10-dimensional Minkowski space, where the conformal field theory involves 10 scalars and 10 fermions in the usual way. If instead we looked at strings in a background space-time with a background metric G bar, then the free theory would be replaced by the free superconformal field theory would be replaced by a nonlinear sigma model with target M and a metric and possibly other fields turned on, but I'll just focus on the metric dependence. Then the free graviton action becomes that for a graviton propagating on this manifold, coupling to this background metric. Here, del bar is the connection for G bar. And this is background dependent. This depends on the choice of background. A background independent action is of course obtained by going to the Einstein-Hilbert action. Constructing a nonlinear action, it just depends on the sum of the background plus kappa times the perturbation. This, when you expand it out to linear order in quadratic order in H, gives the action on the last slide, but it gives plus non-polynomial corrections. But then this has both a diffeomorphism symmetry and a shift symmetry, and a linear combination of these gives a transformation in which the background's invariant and H transforms in this way. And this is a bit like the exotic this is going to be the where some of the exotic diffeomorphisms come from. But in this case, it's not an independent symmetry because it follows from these two. So for the free superfield, the gravity coming from the string field theory in a background, we get the covariantization of the action we had before. So this, now we see that written in this covariant way, it's invariant under the diffeomorphism symmetry, which is in fact inherited from the sigma models diffeomorphism invariance. So these all transform covariantly as one would expect. But there are two further spin 2 gauge symmetries, provided the background is Einstein, given in this form. And so these two are just two independent spin 2 gauge fields. But the lack of background independence means that these can't be related to diffeomorphisms in the way you can in the nonlinear theory. So at this stage, they're independent. This theory has got it's got a background diffeomorphism symmetry plus two gauge symmetries. Sorry? Yeah, so because it's background dependent, this doesn't have shift symmetry. And now, so this action, this quadratic one, doesn't have shift symmetry, but I'm now going to modify it so it does. So the full Sen theory replaces this part of the action by the shift invariant action, which is the full nonlinear action. So we get the Einstein-Hilbert action for H, but it keeps the linear action for the other one. So part of it is sort of background independent, but this part is not. It's still taken quadratic. As we saw, the Sen field theory is non-polynomial for one of the fields, but is quadratic, just quadratic in the other. And that's what gives rise to H appearing non-quadratic, non-polynomially, and H hat appearing quadratically. So if we look at the symmetries, it's got diffeomorphism symmetry, which, as one would expect, but it has exotic diffeomorphisms of two kinds, one like for which the H transforms and H hat doesn't, and one the other way around. And these transformations are the ones which Marmot and Sieback called exotic diffeomorphisms. They're not diffeomorphisms because this field is invariant. These are the real diffeomorphisms. But because there's not background independence, there isn't a full shift symmetry. And so one can't relate these to each other. So you've got a theory which has got all of these different stories going on. And before talking about the resolution which we're going to talk about is making this one nonlinear, and then one regains shift invariance plus an understanding of the relationship between the exotic transformations and the diffeomorphisms. But before doing that, let me say a bit about what happens in the Ramond-Ramond sector. So far the stories looked as if you've got two independent strings which really don't talk to each other. But if you look at what's happening in the Ramond-Ramond sector, one sees that the two are, it's not quite that simple. So going back to the story of the self-dual gauge field in 10-dimensional Minkowski space, then Marmot and Sieback looked at calculating what happens for the action. And one sees that this string field gives rise to a self-dual 5 form, and the other gauge field gives rise to a 4 form, which I'll call A tilde, and it gives an action which looks like this, plus corrections involving coupling to the metric. And this action to lowest order in H, they argued, is precisely the same as Sen's action for self-dual gauge fields. So I've recently been analyzing this story with Neil Lambert. This action could be simplified by shifting F, and then it just takes this simple form. So it looks like a topological BF theory with two flat connections, except when one has to remember that this F primed is self-dual. The shift here is by something which is self-dual. But now the field equation for A tilde implies that F primed is closed, and so it's locally there's a potential A prime for it. Whereas the field equation for F primed implies that the anti-self-dual part of dA tilde is 0, which implies that the field strength dA tilde is self-dual. So in this way, it gives rise to two self-dual gauge fields. And this is a rather interesting system which we discussed in the paper which should be out next week. It's a 10-dimensional conformal field theory which could be thought of as a higher dimensional analog of the beta gamma system. Sorry, there was a question? They're both self-dual, and that's exactly what happens in Sen's theory. So, other approaches would give one self-dual and one anti-self-dual. So this is different from some of the other approaches people have tried. For the coupling to gravity, it turns out that F couples to the graviton H and F tilde does not. And so F transforms under exotic diffeomorphisms of the kind we talked about. And it turns out that there's the physical object turns out to be F plus some corrections involving the graviton. And the full field equations are that this G is self-dual with respect to the physical metric G, whereas F was only self-dual with respect to the Minkowski metric, which was first introduced. So what one's interested in is a field which is self-dual with respect to the physical space-time metric, and this is what this does. And these corrections are very interesting and very important. Sen constructed them perturbatively, and then Neil Lambert and collaborators looked at this, found a closed form for this. In my paper, I replaced the background Minkowski metric by another metric, so as well as having this, so we would end up with this being self-dual with respect to one metric, the other one with respect to another one. And it's rather remarkable that one can couple these two different gauge fields to different metrics and still end up with a covariant theory. And this construction now involves two metrics, and the geometry of constructing this involves some novel biometric geometric structure, which would be a whole other seminar. But the upshot is we've got a physical sector consisting of the physical metric and this gauge field coupling to it, it's self-dual with respect to this metric, and a shadow sector which couples only to each other and not to the physical fields. This field is self-dual with respect to this metric. And this extends to all the other Ramond-Rouon fields by just simply taking F and A tilde to be formal sums of forms of different degrees. And in this story, the interaction between psi and psi tilde is crucial. And without that, one wouldn't be able to get the self-duality. But nonetheless, the physical fields G and F tilde which result do not interact. So with this motivation, this suggests what we should be looking for in generalizing Sen's theory. So Sen's theory was non-polynomial had non-polynomial interactions with psi. It was quadratic in psi tilde. And this led to a theory which was non-polynomial in the real graviton and quadratic in the fake graviton. And so for the gravity sector, there's a natural generalization of this, which is having the Einstein-Hilbert action for both sectors, adding non-polynomial interactions for H hat. And so we have two actions, so H interacts with itself, H hat interacts with itself, but they decouple from each other. And the minus sign here means that this one has got the wrong sign. But this would be fully background independent. It would just depend on the total metric here and the total metric here. And this would then lead to a relationship between the gauge transformations for H and H hat and the diffeomorphisms of the theory. So after a lot of work, the action is, the new superstring field theory action is this. So the first three terms here are Sen's action. So there's one new term which involves a new coupling kappa hat, which would be this coupling kappa hat introduced here. And as one might expect, it's a similar form to the interactions for the physical string. But it's perhaps a little surprisingly, it involves this combination of the original string and this psi tilde string, involving this picture changing operator arising here. Then after a bit of work, linear combinations of the field equations give the same form for both psi hat and psi. And these are both very similar in form to the one, at least for the Neuer-Schwarz sector, to the bosonic string. And so it'd be expected they would include nonlinear gravity in the same way. So we get two copies of an interacting superstring, each self-interacting but not interacting with each other, at least at the level of the field equations. So we get a physical string decoupled from the shadow string, and perhaps I should have put a psi hat here rather than a psi tilde. It has two gauge symmetries, both of which, one which starts off with delta psi is q of a string field lambda of ghost number one, and another one which for psi tilde, where this lambda tilde has got ghost number one, but lambda and lambda tilde have got different picture numbers, so that these things are of the same form. And here, the transformation of this psi tilde involves a surprisingly complicated form. But then, if one goes, so here's the two gauge transformations written again from the last slide. But if one looks at the transformation of this linear combination, then these two equations simplify dramatically, and we get the transformation of psi hat is of the same form as the transformation of psi, but where we define the parameter lambda hat here as being this. And so here we see that we're getting a remarkable structure where we've got this doubling, and the real diffeomorphisms will then, from what we've seen before, will be included in the diagonal subgroup in which the two parameters lambda and lambda hat are equal. Well, they have different signs in the action, so it's not a symmetry of the action. There isn't, if they both had the same sign, we could talk about rotations or a Z2 symmetry, but at the level of the action, it's not a symmetry. But there's clearly a formal, at the level of the field equations, interchanging psi and psi hat clearly interchanges the two, and the field equations have that symmetry, but not the action. So now I want to say a bit about background dependence and independence and how that fits in with the story of the gauge symmetries. So backtracking to the theory of a graviton in a background G bar, if we looked at the linear theory, it was background dependent, and then there was the background independent action if the action for the graviton in the background of the background metric was in fact an action of the total metric G bar plus kappa H, and that was achieved by going to the Einstein-Hilbert action. It was also true if one looks at Einstein-Hilbert plus higher derivative corrections. So for the bosonic superstring field theory, one would expect a classical solution psi bar of the equations of motion to correspond to choosing a consistent string background and hence a superconformal field theory. This superconformal field theory would then have its own BRST charge and its own set of brackets. And one could then use the machinery I've talked about to construct a superstring action for that background using this BRS charge and these brackets. And there's two issues about background dependence. One is the generalization of this. The action has background independence if it turns out to be just a function. So here I'm talking in the context of the bosonic string, so there's just one string field. It will get a little more complicated when I look at the superstring. So it's background independent if It just depends on this linear combination analog of this. But an important part of this is checking this expectation, and that involves looking at a marginal deformation of the conformal field theory, and hence a marginal the corresponding deformation of the BRS charge in the brackets, and showing that that corresponds to a shift of the background solution of the string field theory from delta bar, from psi bar to psi bar plus a small piece for an infinitesimal deformation. So let's first of all look at the second part. That's the rather non-trivial to show. So it's showing that the string field theory defined by the marginal deformation of the conformal field theory and the string field theory defined by shifting the background are the same thing. In other words, they're related by a field redefinition. And that's a rather complicated calculation, which involves in getting into the details of how one constructs the interactions from the conformal field theory. And this was shown for the bosonic string field theory by Sen and Sviebak, and for the super one, for Sen super one by Sen. So I'm going to now focus on the properties of the classical string field theory action and this action of background dependence. So this is true for the bosonic string field theory, where the definition of the new supercharge, of the new BRS charge, is just given by the old one plus corrections involving the bracket of the field with the background. And the new brackets in this background are of this form. So they involve, again, brackets of the fields with the background. But this is false for Sen's superstring field theory. It's false for the action, although it is true that the field equation for psi is background independent in this way. So it has a partial background independence, but the action in particular is not. But for the new superstring field theory that I introduced, it is true. If one has a background psi bar satisfying this equation of motion, then the string field theory defined in this background by formulae similar to the ones I showed before has this background independence. So here for this formula, I've set the two coupling constants equal. If I kept them different, there would be a more complicated equation. So in this sense, this theory has background independence, and this is what one would expect from the analysis of the gravity actions. We saw that for Sen's superstring field theory, if one looks at the gravity action, because one of the actions for the graviton is for the graviton H is the Einstein-Hilbert one and is background independent, but for the other one, the shadow graviton, it's not background independent, and that background independence was achieved by going to the new superstring field theory action. Sorry? Yes. Yeah, so that's a good point. That's a good question. So one of the things which make this, so I've presented the formula in perhaps a deceptively simple way. And if we go back, and what you've picked up on is an important technical point, which is, so here I define psi hat in this way. But the problem is that one can't really invert this to find psi tilde in terms of psi hat. And that means, and that's to do with the fact that there's an issue with defining an inverse picture changing operator, although there are some operators one could define, they don't have all the properties one would want. And because of that, one can't formulate the theory entirely in terms of psi hat. I mean, the formalism is looking as if one would want to write an action for psi and an action for psi hat. But because this operator is non-invertible, one can't do that. And that's why one really has to think of it as a theory of psi and psi tilde in the way that I wrote there. And despite the formal simplicity of some of the equations, there's some deep complications and links between the interactions, which the notation perhaps suppresses, but the point you've raised is a very good one. And that's why I write the action in terms of psi and psi tilde as the independent variables, and think of psi hat as something constructed from those two. So maybe there was another point, but maybe I had a misprint. So, yeah, yeah, yeah. So I think this formula is correct. So basically, this is looking at the action for the string fields in a background psi bar. The background for psi tilde turns out to be 0. And that's related to the fact that when I was looking at the gravity theory, I chose the same background G bar for both of the two gravitons. As it turns out, in the final theory, because of the background independence, I could have gone back and then introduced a different background metric for G and another different background metric for G tilde. And then the formula would have been more complicated. But it turns out that in the superstring field theory, what choosing a background does, choosing a conformal field theory does, is it chooses a background for psi and not for psi tilde. Once one's got a background independent formulation, one can then ask about whether one could use a slightly more general story. And there is a generalization of that, but then it turns out that then one's introducing two sets of brackets, one for psi and one for psi hat. So if one goes back, there we go. We got two decoupled field equations, but here I was using the same bracket here and the same bracket here. And the kind of deformation which I've been talking about is introducing a background conformal field theory which would change this bracket and this bracket in the same way. And that corresponds to a deformation, it turns out, where you don't introduce a background for psi tilde. There is a generalization of all this which I haven't presented, where one introduces a background for psi tilde, but then that would mean that this bracket was different from this bracket, and they would be looking at setting these things up in different conformal field theories. And that's not something which is, although that's taking the same theory but writing it in an unnecessarily complicated way. But it's possible. Well, how long do I have? Okay, so one brief other thing is some related work I've been doing with Neil Lambert. I've talked about Sen's approach to chiral gauge fields. It also applies to chiral bosons in 2 dimensions. So there's a Sen-like action which will involve 2 world sheet metrics instead of 2, G and G tilde. And so, for example, in applying this for the heterotic string from the world sheet point of view, where there are 16 chiral bosons, then the partition function for the chiral bosons famously depends just on holomorphically on the modulus on the world sheet. And this can be thought of as a holomorphic square root of the partition function for non-chiral bosons, which is the modulus squared of this. In the two-metric formulation, there are two metrics, one which, the physical one, which has a modulus tau, and the shadow one, which has got a modulus which we'll call rho. And it turns out that the partition function which results from that story gives rise to a function of tau times a function of rho. So this two-world sheet formulation naturally gives a way of picking out a holomorphic square root. And to get modular invariance for both tau and rho involves in adding extra fields to couple the lack of modular invariance just from the chiral bosons. For the tau, it constructs the rest, means introducing the rest of the heterotic string. And for the rho, it means introducing a shadow heterotic string. So it's amusing that from this point, the world sheet point of view, again, looking at a formulation, an action formulation leads to a doubling, and it leads to precisely the same doubling which arises from the extension of what I've said for type 2 superstrings to the heterotic superstring. So let me now conclude. I've constructed a new superstring field theory which agrees with sends for the physical sector and so gives the correct superstring amplitudes. And it gives two copies of the superstring, each of which is self-interacting but not interacting with each other. And the new superstring field theory has got two stringy gauge symmetries, one giving exotic diffeomorphisms in the physical sector, the other giving exotic diffeomorphisms in the shadow sector. And the real diffeomorphisms are in a diagonal subgroup and act on fields in the usual way. And the fact we've got three kinds of symmetries, one of which is the real diffeomorphisms, well, the two independent ones. And the reason you've got two independent ones is tied in with the fact that you've got two independent metrics for the diffeomorphism-like symmetries. But then these extend to all the stringy symmetries. So there are two B-field symmetries, and so on. So I've argued that the new theory is background independent in the sense that I've described, and I've shown how that works in detail for the graviton sector. And it's interesting that this story involves a novel bimetric geometry, a story with two metrics, which enables more kinds of structures to be written down, and that's seen explicitly in the kind of complicated actions which arise for the Ramond-Ramond gauge fields. And this incorporates this doubled symmetry. And in particular, there's the symmetry, the gauge symmetry from the string field theory point of view has got two copies of the L infinity algebra, one acting on the physical string field, the other acting on the shadow string field. So there's a lot of questions, I think, which remain. One is whether this kind of doubling, which formally seems to be very effective and very useful in giving a very powerful formalism, whether that's essential or whether it's just a reflection of the baroque nature of the NSR formalism. And there's a question about whether there's a better way of doing this which doesn't involve doubling the two sectors. But I think, nonetheless, this now gives a picture which seems to work, where one's got a beginning of an understanding of the symmetries and the relationship to diffeomorphisms and the other gauge symmetries one would want to understand. And the background, and one of the ambitions of this approach is to try and find an understanding of the geometry behind the background independent action, just as Riemannian geometry gave an understanding of why the why the Einstein-Hilbert action works and why it's such a powerful construction. So all that's for the future, and I'll stop there. Thank you. Yep. No, it's the same, exactly the same action. What all that differs is the GSO constraint, which is imposed on the GSO projection, which is imposed on the string fields. And what that comes in is giving a democratic formulation for the 2A Ramond-Ramond fields, where one has, if one goes back, so here I wrote this down for the 2B story. The 2A story, this F would be a sum over even degrees and A tilde over odd degrees. And this gives it a formulation where one has a democratic formulation of both of those. An interesting question is whether there's a formulation that's 2A string field theory which doesn't involve the doubling. And there, I think one of the key issue is the problem of constructing a kinetic term for the Ramond-Ramond fields. Because one can write down psi tilde cubed psi, but one can't write down psi cubed psi. It doesn't, that would just vanish in the way that things are defined. And so at the moment, there isn't any better way of doing the 2A theory. But this approach of SENS, I've concentrated on the 2B, but applies equally to the heterotic and the type 2A. Yeah.
One of the pioneers of that too. So the question is whether the ODD implies this doubling, or it's like not really a question. And it also this ODD may have some implications or some comments on the negative sign of these two things that you have, and probably that's what is needed to have the ODD.
Yeah, you're quite right. This whole story has got formal similarities with many other interesting stories. I think one of the key issues is in the current formulation, there's no way in which the two sectors talk to each other. They're not interacting. And so, there's a question about whether there's any meaningful kind of story involving an enlarged formalism. I mean, in the ODD story, a key thing is that there's interactions between the two sectors, and that means it gives a very non-trivial structure.
Well, actually, the issue starts when you use psi and psi tilde on not equal footing, so you put the background 0 for one of them. But ODD tells us that this is not the right way.
Yeah. So it's interesting that if one restricts the Nevers-Schwarz sector, where this awkward picture-changing thing, non-invertible picture-changing operator is not there, then things become much simpler and there's much more structure which emerges. But a lot of the most interesting structure and the most non-trivial part involves what goes on in the Ramond-Ramond sector. And it's that side of things which is kind of rather novel and non-trivial. And so with the what transform the, yeah, okay, yeah, yeah. Yeah, so this story is where you're looking at these things. These can also be thought naturally as I think you're alluding to, these arise from bispinors in the NSR formalism. but it can also be thought of as being a spinner of an ODD, of an O1010 transformation. And again, that's very suggestive. And so these kinds of expressions could all be rewritten in spinorial language. And in fact, these originally were found from the where these arose as bispinners rather than as forms within one.